we develop our real number system, what we are interested in is having some assumptions or some postulates or what the book calls axioms that we are going to assume to be true. Is that right? So what I'd like to do is to start looking at some of these axioms. Let's look first of all at a set of axioms that have to do with the operation of addition, all right? And let's call them axioms of addition. And let's see if we can't make a list of these, and in fact we then can make a similar list for the set of axioms of multiplication. Let me use our notation that I have introduced the other day. For every A and B and C belonging to the set of real numbers, all right? And let's see now how we may make a list of these. Now if we had a real number A and another real number B, and if we were to add these two numbers, what we would like to have is a third real number, and in fact a unique one. We will always have the same and unique number, which is also going to be what kind of a number? And it's also going to be a real number. And this property is given a special name, and does anyone remember it, Doug? This is called closure, C-L-O-S-U-R-E, all right? Good. And then, of course, if we had any two real numbers, A and B, if I were to take A plus B, this is the same as B plus A, and the name that we have given this property, this axiom, Peter, is called the commutative, C-O-M-M-U-T-A-T-I-V-E. Notice I'm spelling this word because of all of those little hash marks in there. And let's see now, if we then were to take any three real numbers, A, B, and C, if I then looked at A plus B plus C, we know that the resulting number that we have is the same as A plus B plus C, and we have given this a special name, which we called him the associative property, or the associative axiom, with respect to this operation of addition. All right? Now, let me use our symbol of there exists. All right? There exists some number, which we have called 0, all right, in the set of real numbers, such that, and if I were to take some element A, some number A, and add 0 to it, we end up with what element? What number then do we have, Tom? A itself. And of course, if we were to write 0 plus A, we know that this is equal to A. And we have given this number 0 a special name. And what is that name, Don?
The identity element.
And this is called the identity element with respect to this operation of addition, okay? The identity element. And once we have that identity element, what we would like to do then is to have some number. There exists a number which I will write as the opposite of A, belonging to the set of real numbers, such that A plus the opposite of A is equal to, and Peter?
0
is equal to 0. And we may also write the opposite of A plus A is equal to 0. And what name have we given this element of the opposite of A? Brenda? That we call, does anyone happen to remember what the name of that is, Malcolm?
Additive inverse.
This is called the additive inverse. Let me just call it the inverse element with respect to the operation of addition, all right? Now notice the wording that I used there, in which I call this the opposite of A. Please don't get into the habit of calling this negative A, because if A itself happens to be a negative number, the opposite of that negative number is going to be what? It's going to be positive, and if A itself were positive, then the opposite would be a negative number. So please think of it as the opposite of A rather than negative A. Okay? Now notice we have these 5 properties with respect to the operation of addition, and there's a nice duality that I think we can establish in which we'll have some operations or some axioms with respect to our operation of multiplication. All right? Again, for every A and B and C belonging to the set of real numbers, all right, if I have some element A, some real number A, and another real number B, and if I were to multiply them, what we would like to have, in fact what we insist on having, is a unique number, which is still what kind of a number? It's still, Michael? It's still a real number. This then belongs to the set of real numbers. And let me not have to write the word closure again. And we know that this is our property of closure with respect to the operation of multiplication. Okay? And similarly then, for every A and B belonging to the set of real numbers, A times B we know is equal to, and Don? B times A, and we call this our, Malcolm, our commutative property with respect to the operation of multiplication, all right? Again, for every A and B and C belong to the set of real numbers, A times B times C is the same as A times B times C, and we give this property a name, Glenn? That's our associative property with respect to multiplication. Now, again, notice the duality that exists between the operation of addition and multiplication. And in this case, with respect to addition, there exists some number which we call 0, which is its identity element. And there we would like to have, there exists some element, and in this case, what is that number going to be, Doug? 1. There exists some element which we call 1 belonging to the set of real numbers. I'm going to insist that this element 1 is not the same as that element 0, okay? Such that, and now what would we like to say? We'd like to say what? A times 1 is equal to A, and in fact, we may also write it as 1 times A is equal to A. The reason I am including this, it looks like a commutative property built in there, is that as we go through our proofs, there'll be times when we would like to think of it as A times 1. There might be other times in which we want to think of it as 1 times A, and in this case, we have it right within our axioms, okay, so that we don't always have to talk about commutativity. Well, here we have this element 1, which is the identity element with respect to multiplication, is that right? And once we have that identity element, what we now would like to talk about is some element. There exists some element, which I may write as 1 over A, belonging to the set of real numbers. In this case, the element A cannot be equal to 0, okay, such that A times 1 over A we know is going to be equal to, Michael, 1, the identity element, and in fact we may write 1 over A times A is equal to 1, okay? Again, there is another name that we give this. Of course, well, one of the names that we have given it with respect to our duality here might be called the, Doug? The multiplicative inverse element. And I think there was another word that we used to describe this, Glenn, called the reciprocal. All right, let's include that here. The reciprocal of a given number A, okay? And again, this is unique. For every element A except 0, 1 over A is called its reciprocal or its multiplicative inverse element. Now notice we have 5 axioms with respect to the operation of addition, and here we have 5 axioms with respect to the operation of multiplication, and there's one axiom that pulls the two together. And what is that axiom that you are familiar with, Tom? The distributive axiom. Okay, let's put it up here, in which we have the distributive axiom. All right, the distributive axiom. Actually, I think we'd better say a little bit more than simply the distributive axiom. And what do we want to say?
Back to multiplication.
Okay, let's write it of multiplication. And there's a word, I think, perhaps, which might be descriptive here. Multiplication over addition, all right? Over addition. And let's see how that goes. For every A and B and C belonging to the set of real numbers, all right? And what then can we say? Well, let's write it as A times B plus C. And here's where you get the idea of multiplication over addition, all right? Is then going to be equal to, how may we say this, Bill?
AB plus AC.
A times B, let's actually include this symbol with some parentheses for emphasis, plus, and you say A times C, all right? Now, I wrote this in that pattern, but I think we may also write it. Let me include the pattern of B plus C times A, some sort of a right-hand distributive property, if I may, in order to avoid this business of going through commutativity every time, okay? It's going to be equal to, and now here we have B times A plus C times A, all right? And you may think of this as our distributive property. It's one property, but written in these two patterns. Okay, very nice. Now here we have these 11 properties. There are these 11 properties that hold true for our set of real numbers that we have thus far, all right? Now, there are one or two other ideas that I think we can look at. Let me come back to this idea of taking a number A and another number B And with respect to closure, our property of closure, we have said that if we were to add those two numbers, if we were to operate on them, in this case we can add, or else in fact we can multiply them, all right, we're going to get a unique number, a third number, which will be unique, which is itself a real number. It's still a real number, is that right? Now notice, I'm taking two numbers to begin with. And suppose I had three elements, A plus B plus C. Well, if you were to add three numbers, 2 plus 3 plus 4, you can't add all three of them at the same time. You can add, say, 2 plus 3, and that gives you an element, which happens to be 5, and then you take that element, 5 plus 4, and then that gives you finally your number 9. So we can indicate that in this pattern, in this fashion of simply putting some parentheses here, plus C. And this is our definition of what we mean by the sum of three numbers. And what characteristic do our numbers have here, or do these operations have?
You operate them binarily.
They are, all right,
Binary
good.
operation.
Let's call this a binary operation. In other words, addition is certainly a binary operation. We can only add two numbers at a time. Is that right? And of course, we can also simply multiply two numbers at a time. Or suppose we happen to have had four numbers that we would like to handle. Okay, we now would like to add these. So you say to yourself, well, let me add the first two. I can indicate that by this set of parentheses. And then to that number, I want to add a third number, call it C, and that gives me another number. And then finally, to that number, I will add the number D. Okay? And we define it this way, in which we can simply add. Similarly, we can continue this on for as many numbers as we want, and also we could write the same kind of a pattern with respect to the operation of multiplication. So this is a binary operation. Later on, in fact, we will operate on one number. I don't know that you can think of any operations on one number. Well, in fact, the square root, for example, the square root of 4. There you are operating on just one element, 4, which you know is the number 2, or else you can square a number. That may be thought of as a what? This is a binary operation, and what then would an operation be if we're talking only about one element? Well, it's called a unary operation. Let's see now. There is perhaps another property that I think we should look at. Suppose we had a very simple little statement such as 2 times 3 plus 4. All right, here's an expression. Now, you and I have come up with another name for 2 times 3, which we know is 6, and then we still have plus 4, and we have another name for 6 plus 4, and notice in each case we're saying that this is equal to. In other words, we have substituted another name for some numeral here, or for some expression. And there's a principle, so what the book calls a principle, which enables us to do that in Glenn. It's called the substitution principle. Good. And we're going to be using this quite a lot as we go through our work this year. Let's actually write out a statement which says what this example is illustrating here. And how may we say that? Well, let's write as any equivalent. Let me use the word equivalent number or expression. Let me use the word numeral, perhaps. Any equivalent numeral, okay, may be substituted, CED, for a given numeral, all right, for a given numeral without changing its value. Is that really what we're saying? Okay, for a given numeral without changing, a lot of words, but it's a very simple idea, without changing its value, okay? And we think of this as our substitution principle. Well, I think there's one last idea that we should look at, and it has to do with our relation of equality. And again, let's call them axioms. Axioms of equality, in which you have been using these axioms all along, probably since your first work in mathematics. And one of the statements simply says A is equal to A. For every number A is equal to A. And this is a relation of equality here, in which we have this this particular property that holds true. And does anyone happen to remember the name of this, Rick?
Reflective.
This is called our reflexive axiom or our reflexive property, reflexive, okay? Now, perhaps it's not too obvious as to why this would be considered important. Only if you were to think of an example, if you could think of some relation in which it is not true, perhaps then you would realize the significance of when it is true. For example, the relation of inequality. A is greater than A happens to be what? That's false. The relation of is a brother of. Let me just get it out of the context of mathematics. Is a brother of. A is a brother of A. Well, that certainly, you're not your own brother, would not be true. All right? There's a second property in which we may say if A is equal to B, then B is equal to A. And we gave this a name. Does anyone happen to remember that name, Charles? Bill?
Symmetric.
This is called our symmetric, S-Y-M-M-E-T-R-I-C, our symmetric property. Is that right? Is this what I want to say about the symmetric property, Don?
That's supposed to be substitution up
Where? The
there. On E and when you wrote it on again.
S-U-B-S-T-I, oh boy, thank you very much, S-T-I-T-U-T-I-O-N. All right, do I have enough scribbles in there? Good, that's all right. Fine, I hope we can all read that. And similarly, maybe substitute, S-U-B-S-T-I-T-U-T-E-D, okay? There's a T in there, everyone can see that T, right? Good. Fine, thank you very much, Don. How about then a third axiom of equality, in which if we may say, if what? If A is equal to B, and B is equal to C, then what is our conclusion? But, Malcolm?
A equals C.
You'd like to say that A is equal to C, and we have given this a name. Does anyone remember that, Michael?
Transitive.
This is called the transitive property of equality, okay? The transitive property of equality. Notice with respect to, say, inequality, if A is greater than B, and if B is greater than C, then A is greater than C is also true. And we'll get into some of the properties of inequality later on. Well, these are some of the axioms of our real numbers. Later on, we're going to pick up a few more of these axioms, and on the basis of these axioms, we then will go ahead and prove some theorems, and that's how we're going to build up our system of real numbers. Let me give you your homework assignment, and I think that's all we need to do for today.